Okay, so our next speaker will be Martha White. She's an assistant professor in the Department of Computer Science in the University of Alberta. Her primary research goal is to develop technique for adaptive autonomous agents learning on streams of data with applied focus on computational sustainability. So her talk today is going to be on planning and reinforcement learning with learned models in Dyna. Unfortunately, she has a schedule conflict, so we are going to give this talk online. And now I'm just going to set up the talk. Okay.
Do you have my hands on here?
Okay. Yeah. Oh, wait. There's no sound, I think. Okay. Okay.
There's no sound?
Okay, there's sound. I think there's sound. Okay.
All right, I'll lose. So is there too much feedback? Okay.
It's good. It's good. Yeah.
Great. So I just wanted to say hi so everyone can see my face, and I really appreciate this opportunity to tell you a little bit about Dyna, even though I'm not actually able to be there with you. And I really enjoyed these landscape talks. So at this point, I'm going to switch the slides, and you will no longer be able to see my face, but I'll still be able to see you, and I'll try to respond to questions. I'm going to try to make this talk as interactive as possible as I can be over Skype. So let me share my screen now. Okay, so presumably you can see my slides now. If you can't, tell me, do something about it. Okay, great. So a lot of the talks I noticed for this workshop are about using generative models for exploration. I think it's a really important topic, but there's actually also another place where we can bring in knowledge from those working on generative models, and that's actually for planning. Particularly, I think this is an exciting direction to do within Dyna. So what I'm going to tell you about first is just what Dyna is. I don't expect everyone to know what that is, and I'll give you the high-level message after I just give you a brief explanation of Dyna, and I'll kind of dive into some of the experimental results that we have that show that some of the conclusions we have from using learned models in Dyna. Okay, so let me just tell you what Dyna is. So Dyna is this planning paradigm. There's lots of different ways to do planning with models in reinforcement learning, but I think this is a particularly elegant one, and one that has been somewhat underexplored. So, now what is Dyna paradigm? Here you can imagine that you still have an agent. It's learning a policy or a value function. You can using whatever your favorite action value learning method or policy learning method. Let's say you have your Q learning update. So you have the standard direct RL setting where your agent is getting real experience from the environment and is doing direct RL updates, say with something like Q learning. But then at the same time, it wants to use that data a little more efficiently. So it's also going to need real experience to learn a model, and then it can actually start generating simulated experience from that model in the background. So this is going to try to be more sample efficient by taking advantage of the fact that the model summarizes some of the past information and lets you re-simulate important state. In addition to direct RL updates, you'll also in the background on some state and action ask your model, what is a possible next state and reward? The state and action might be a real state and action you have in the world, and then you're going to simulate some hypothetical next state and reward that's this pink color, which may not even be a real state and reward. But then you're going to do an update, a standard Q-learning update. Let's say if you picked Q-learning as your direct RL update, where now this TD error delta is just based on this simulated experience. So it's a very natural architecture. You could just add in a model into whatever policy learning or value function learning algorithm you have. And now the two key components really in Dyna is first, how do you do the search control, how do you put state in action? But one of the real biggest part of the focus has been how do we learn good models? So how do we get this model from real experience so that it's actually useful to simulate experience from that model rather than just doing direct opt-out. So the focus within planning has typically been to improve the learn model, although actually learning models within Dyna has been, like I mentioned, kind of underexplored. Okay, so that's the general Dyna paradigm and the focus that's typically done in Dyna. And let me just give you the high-level takeaway. And actually, one thing before I tell you the high-level takeaway is that we actually are getting better at learning models. We had this exciting new time where we can actually produce useful models in complex domains, like some of these nice models that I've learned in Atari, where you can do pretty far step predictions into the future. But some of these advances in model learning don't seem to really have translated into advances in using those models within planning. And there's kind of a question of why that is, and if it's actually possible to get models to be helpful within planning. So one of the high-level takeaways that I want to give you is that using learn models inside Dyna as planning formalism actually can improve data efficiency. So this feels like an obvious conclusion, but actually the other key insight is that using learn models is not automatically going to give you wins. What you really have to do is be careful about how you're going to use that model. So not only do we have to care about having reasonably accurate models, I mean, you're not going to be able to take advantage of very inaccurate models, but given a reasonable model, even then we have to be careful about the search control question. So it's really critical for a model to be effective to actually be careful about what states we sample from. Okay, so if you get nothing else out of this talk, really that's kind of the key insight I want to get across to you. If we want to make model learning effective for planning at RL, we really got to focus on the question of where are we going to sample from. Okay, so now I'm going to kind of go through a little bit more depth. I'm going to tell you a little more about why Dyna is a useful planning paradigm and some of its properties, even though it's been somewhat underexplored. And then I'm going to show you a few experiments demonstrating this key insight, and also a little bit of how we're going to learn models for Dyna, and what I think are important properties for learn models in Dyna. And I'm going to kind of leave it as an open question to all the people who do generative models, then what kinds of useful generative models we can use specifically within Dyna. Okay, so just to give you a bit of a background, there's lots of different planning strategies, and I just wanted to highlight a few here. A lot of the work in planning is often trajectory-based, where you learn a model for your environment reinforcement learning, and then you generate rollouts, and you can use those rollouts for Monte Carlo planning or trajectory optimization with more traditional control methods. So a lot of the work has been around generating trajectories with your model and then using that for planning. There's also this whole class of work on approximate value iteration, where you do learn approximate models, and then, for example, go and approximate your action values from the approximate models. And really, Dyna can kind of be seen as an example of approximate value iteration, but a lot of these strategies that have been taken, like stochastic factorization and these nice kernel mean embedding strategies, don't exactly have the same flavor as Dyna. So lots of different planning strategies out there, and then let me tell you why I think Dyna is a really promising direction forward, and actually one of the easiest planning paradigms to take in advances from the generative models community into reinforcement learning. So really I have kind of 4 main advantages of Dyna. I'm going to go through them, and then I can continue from there. So just telling you up front, there's going to be a before. So one of the nicest things about Dyna is that, as opposed to some other planning formalisms, it really nicely interleaves learning and planning. So what this means is that the agent can actually act quickly. It has a time scale given to it by its world. So, it has to take actions now. And it can do that by its direct method. So it has a policy or it has a value function, and it can quickly make decisions, as opposed to some other planning methods, which actually have to do planning right now in order to take an action. And that can be slow. But then agent that can still take actions fast in the world, and then it can use whatever computation it has in the background to actually do as many model or as many planning steps as possible. So depending on the situation, you have this nice adaptive planning, where on some steps maybe you have to act fast, so you can't do too many planning updates, and on other steps you can actually make decisions a little slower, and you have more time to do a bunch of planning updates in the background. So it's this nice way to take whatever leftover computation you have and just use information from your model to get better action values or to get better policies. So it very naturally works well for adaptive agents. So that's one of the reasons I think Dyna is a good planning formula. In a similar way, because you can kind of just take whatever computation from the model is just supplementing your direct RL agent. Again, either learning action values or policies. So again, if you have just a model that is accurate in some part of the world, you can still take advantage of that model to improve your action values, even if you can't take advantage of that model everywhere in the world, which would not be true for some planning methods that rely strongly on the model being accurate everywhere. Okay. So another really important advantage of Dyna is that we can avoid multi-step rollouts. So I mentioned a lot of methods do use trajectory-based approaches where you roll out many steps into the future. But in time series prediction and in general for these dynamical systems, that iterated predictions can compound errors. And then in addition to compounding errors, it's going to produce these implausible states. So this is something of a problem. And I'll just use this nice example from a collaborator, Eric, who's given me permission to use this image, about how outrageously bad predictions into the future can be if we start iterating our models forward. So the first line here is an example of this little shooter game of a real sequence of states in the world. There's a little shooter at the bottom of the screen is the agent. It has to try to hit this bullseye. And the bullseyes actually move as time passes. So you notice the white dot in the middle of the black square is the bullseye, and it's moving back and forth. Now the agent gets the screen as its input, and it can use that to learn the model. And the lower line is the best model the agent can learn with the screen that is given to it as input. Okay, so the first step prediction is already a little wrong. It can't perfectly predict that there's no bullseye. So you can see here that there's these red squares indicating that it didn't predict correctly. And this is already a little bit wrong, but it's not too bad. And as you start iterating, it gets more and more outrageously bad. So there's some nice work about trying to mitigate these rollout errors, but Dyna takes a different strategy, which is not to do rollouts at all. But it's still in some sense implicitly doing multi-step rollouts, because by using things like bootstrapping, for example, if you do Q-learning, you're generating only one-step transitions, but you're bootstrapping off of your action value estimates to really make these more long-term updates. So it's taking advantage of the fact that we know our algorithms can do well with one-step transitions because they are designed to do so. I'd also like to mention that you technically can still do more long-term planning by using the option models. Okay, and the last reason I think Dyna is a nice formalism is that we just need sample-based models. So you have conditional sample-based models, but most of these strategies will need only conditional models. But we don't really need to explicitly estimate densities. We just need to be able to generate simulated experience from our model. Okay, so we have all these nice advantages of Dyna. And I'm just going to take a pause here in case there's any difficulties in terms of hearing me. Is everything still fine?
Yeah.
Is it easy to hear me? Okay, good. Okay, so now we have did you have a question or comment?
Yes.
Okay, all right. So we have all these nice advantages of Dyna. I think, like I said, I think it's a really promising way to go forward. But a natural question is, why are we actually using Dyna? So, there's a few places where people are actually using Dyna, but it really isn't that much. And one of the answers to this question is that we sort of are using Dyna with this thing called experience replay. So an experience replay has been pretty instrumental in getting things like DQ into work. So using Q-learning with neural networks. And the idea of experience replay is very straightforward. You just keep a big batch of data, let's say the most recent batch of data, and instead of just doing stochastic gradient descent, like you do for Q-learning, or like a stochastic approximation, you're actually going to take little mini batches from a buffer, and you're going to replay those better. So this little mini batch strategy makes a lot of sense, and you can kind of think of it like a Dyna-based strategy, because really we're taking our buffer of transitions and we're simulating experience, simulate with quotations, because we're not really simulating, but we're sort of simulating transitions from this experience, and we're using those to update our action values, which is exactly what I said Dyna does. It's still a little different than Dyna fully with a model, because it doesn't have this aspect of having a search control queue, rather it has a buffer of transitions. So we don't really have that much control over what we can simulate. Only thing we can do is a batch of data, a buffer of transitions, and play an entire transition. We can't actually sample from a model like M for a given S and A. maybe that seems like a reasonably minor difference, and experience replay has been very successful in improving training of our models. So again, you still might ask, does this difference really matter? And is it actually going to gain us anything to learn explicit conditional models? Particularly, experience replay is just from the world. Is it worth the potential bias that we get when we actually learn models? So a natural question when we move to asking why aren't we using Dyna, or how can we make Dyna effective, is to ask how much can we gain beyond experience replay, which is a pretty nice and simple heuristic way to incorporate more, to be more data efficient or sample efficient with what you have seen so far. So obviously I wouldn't be giving this talk if I didn't think it was useful to have these conditional models. And I'm going to focus in the experiments on the third reason that learning models is useful, so the querying question. But there's a couple of other reasons why it's pretty clear that a learn model should be more helpful than just storing a transition buffer of experience. One of them is compact. So of course, a model can summarize experience in a compact form. You've actually learned some kind of model, whereas storing a big buffer is not in any way trying to be compact. A more important reason, I think, is coverage, is that we can't actually store all of our experience. We could maybe with our current problems and the size of our computers, we actually can store all of our experience. But realistically, for our artificial intelligence, we're not really imagining that they can store all experience that they've ever had since the beginning of time. So we want to realistically imagine, if we can't store all of our experience, what should we do? And what you typically do is the most recent experience. And then you're really forgetting about large chunks of your space. So we want to keep this coverage property where we can actually query our model, ask our model, what would happen in this part of the space that I haven't visited in some amount of time? And experience replay just won't let you do that because you can't store your experience. Okay, and then the last one is querying. Is that unlike experience replay, where we can just replay transitions from our buffer, entire transitions, so state, action, next state, reward, and gamma, for model, we can actually query a model from a particular state and action. So we can just ask our model, hey, I just thought of this state and action I'd like to know something about, and it can tell us about that. And experience replay will restrict it only to whatever experience is stored. Okay, so this is the part that I think is very important, is the search control question. And I'm just going to give you two examples of explicit things that we do when we explicitly query the model that we can't do if we just do something like experience replay. And there are actually other benefits, but these are the two that we explore in our experiments. Okay, so one of them is that we can actually get predecessor states, and this is not new. It was introduced with prior to sweeping long ago, but it's worthwhile to re-emphasize how important this is for Dyna, because Dyna-style strategies since then don't typically use predecessors. And as I'm going to show you, it's very important, actually. So what is a predecessor? Here, what you might imagine is, imagine someone told you this is a high priority state. So let's say I just entered a state, I see a really high reward that I wasn't expecting. So my TDA error is high, and so in that sense it's a high priority state because I want to update my value strongly for that state. Well, we know that there's a temporal credit assignment in RL, so the states that led into that state should also actually be updated because now our action values have drastically changed for that state. So what we really like to do is generate predecessors that can lead into that state and say, let's go update all of those states as well. And we'd like to query our model from all the predecessor states as well. So what we really need then is a model that says, given I'm in high priority state S, what's the distribution over states such that if I was in a state and I took an action, I actually led into the high priority state as promised. So I need this kind of reverse or predecessor model. That's hard to get from an experience replay buffer, but it's straightforward to learn a model that gives you predecessors. So that's one aspect of where we can query our model to get predecessors. And another intuitive way that we can query our model is to actually ask for on-policy transition. So again, if we're given some high priority state that we think it's important to stimulate experience from, then instead of asking what is the transition under the old policy, which is what your experience replay buffer has, I might ask, what is the outcome for an action taken under my current policy? So I'd like to update more information about my current policy and ask on-policy transitions, which a model can definitely answer for me, and my experience replay buffer may not be able to. Okay, so let me just talk a little about some of the experiments we went into. So just to motivate or remind what's going on here is that I'd like to show first, how can we actually make it so that learned models in Dyna can outperform the most simple baseline heuristic, which is something like experience replay. And so first I'm just going to give you some experiments in grid rules that emphasize how important the search control part is to making it effective to use learned models. And then I'll tell you a little bit about the learned model strategy that we used and why the properties of that type of learned model is actually good for Dyna. Okay, so let me talk about these experiments. We did a lot of extensive experiments in grid rules to start, both tabular and continuous and deterministic and stochastic, because we wanted to carefully do lots and lots of runs and look at the distinction between having the change from tabular to continuous and deterministic stochastic. We used Q-learning with epsilon 0.1, and we fixed the planning steps across all experiments to 5 planning steps. And we kept a buffer size of 1024 and a search control queue size of 1024, and we just let the oldest samples be deleted as time passed. We tried other strategies for maintaining the transition buffer for experience replays to try to give the best chance to develop. We found that a recency was just the best choice for experience replay, so that's what we did for our method as well, to be consistent. Okay, so the way that samples get put on this buffer then is most recent ones, and then when we actually want to sample buffer or search control queue, we tried 3 different sampling strategies to investigate this question: how important is it how we query? So one strategy was random, where you had a buffer of 1024 things and you randomly sampled one item. Another one is to add prioritization. So I mentioned a high priority state. Each transition or state to action in search control queue is associated a priority, and that priority is just the absolute value of the TD error when that point was added to the buffer or search control queue. So a high TD error tells you that maybe you need to update more in that state, and so that state should have a high priority. Of course, many other heuristics can be used for prioritization, but we just went with the one that is still commonly used for prioritized approaches. And then the last sampling strategy is this predecessor strategy I mentioned. So for a learned model, predecessors, straightforward how you might do that. You can't really do predecessors for experience replay, but there is this nice heuristic proposed in the prioritized replay paper, where on every step, when they look at the most recently added transition to your buffer, if it has a high priority, you can look at the sample right before it, the transition added to the buffer right before it, and you can increase that priority. The new priority is higher. So in some sense, it's a limited form of predecessors where you at least bump up the priority of the most recent thing. It doesn't tell you all the predecessors leading into that state, but it at least increases the priority of one predecessor. Okay, so this is the general experimental setup. Now let me just give you the overall conclusions from a lot of these experiments that we ran. So kind of ignore the right side of the screen for a moment. This is just looking at increasing numbers of states and moving from deterministic to stochastic. And I should mention this is in the tabular grid world, where there's plus 100 at the goal and 0 reward everywhere else. This little grid world you can see at the top right here. Okay, so a couple of things to notice that I'll emphasize is there's the dotted lines are all experience replay variants, and the solid lines are all Dyna variants. And this is with a learned model in the tabular case, which is really just a counting model, so it's not a particularly interesting model. But it is with a learned model. Now, if you notice Dyna random and ER random in the top left graph, perform almost exactly the same. Random strategy for your search. Oh, am I cutting? Did I cut in and out there for a second?
Sorry, the connection was off for around 10 seconds before, so maybe you can go back to what you discussed about the experiments.
Yep, sounds good.
Thanks.
Since it was 10 seconds ago, I'll just say the thing that was really important, which is, so ER is the dotted lines, Dyna is the solid lines, and if you notice an interesting thing, that Dyna random and ER random perform almost the same. So just adding a learned model in Dyna, it's not going to suddenly give us improvements over experience replay. And this is not particularly surprising in retrospect, but you might hope that learning a model, putting all this effort into it, should give us something over experience replay. The only way we start getting gains is when we add this Dyna and predecessors. And I should mention that Dyna predecessors
is predecessors plus priorities. And on-policy Dyna here is predecessors plus priorities and on-policy transitions. So actually the on-policy transitions overall don't have that big of an effect, except for in the stochastic case with lots of states. But otherwise the biggest gain is simply moving from adding predecessors to Dyna. Okay, so just in the interest of time, I better go a little faster here. There's really just two main conclusions to take away from these results. One of them is Dyna only outperforms experience replay if we give her predecessors with priorities. So learning the model is worth it if we actually use that model carefully. Okay, and the second conclusion is that actually prioritization added to predecessors is very helpful, but otherwise prioritization actually hurts. And this is somewhat surprising. You would think that rather than randomly sampling your buffer with whatever was your most recent points, it would be better to have priorities associated with those elements, so you sample higher priority elements more frequently. That just seems like that should be helpful. So what seems to be happening with the second conclusion is that the priorities actually get kind of out of date as you update, as you're updating your value function, and so sampling according to your priorities is a bit misleading. Whereas adding prioritization to predecessors are getting generated as soon as you see an important state, and so really their priorities are more up to date and they're more informative that that's a state that you should be updating now. So this is a conclusion that's a little bit separate even from the Dyna question, but using prioritization with predecessors is super great, but otherwise it's a little bit problematic. Okay, and of course we also ran these experiments in a continuous setting where we had to learn a model. And before I explain the model, I'll just show the result. So the model, we're calling it this reweighted experience model. I'll explain in a second. But again, the conclusions are about the same. If we are careful with how we use our model, we get this result that with predecessors it can do better than experience replay, but otherwise it's actually down with these lines of not doing very well with the exact same learned model. So that gap between using the exact same model where one does or does not use predecessors is a pretty large gap, and it shows that maybe we need to start focusing a bit more on the search control question. Okay, so let me move on to the second part then. It's, we have an idea of how we should use our models, but maybe we should talk a little bit about what are some desired properties in about the last 2 minutes that I have. So, we have some idea of what we'd like from generative models, but depending on your planning setting, of course, the properties you'd like from our models will be and should be different. So, for example, if you're doing a trajectory-based strategy, what you really want is a model that is actually going to do well for multi-step rollouts. You want something that's going to correct errors into the future. That's not necessarily something we want for Dyna. So here, I'm just going to lay out some of the properties I think are really important for learned models in Dyna, and then maybe you can tell me via email or however some models you think that are actually would satisfy these properties well, because I'm only starting to learn more about generative models now. So one thing I think is important is this Dyna is interleaving learning and planning. So we really want our models to also be online. We want them to be incrementally learned and adaptive, because we are imagining this online system. It's pretty important for them to be data efficient, particularly in this single task setting, because we're often asking, can I add Dyna to a model-free method? So can I take Q-learning, and can I add Dyna and actually improve upon Q-learning? So in order for that to actually be possible, the model needs to learn fast enough so that it can actually improve data efficiency of the value function learner itself. So data efficiency is really critical for this single task setting. If you're looking at this other model-based setting where you're imagining multiple tasks into the future, you can spend all this time learning a beautiful model so you can do better later. That might be a slightly different criteria. But here we're starting with the question of, I have a task, I want to do better than model-free. Okay, and then of course we'd like to be robust to forgetting, so we know if the agent's going to be going to parts of the world repeatedly, and we don't want to forget about other parts of the world, because we're going to want to query our model in those other parts of the world. And the last thing I think is really important is we want computationally efficient sampling, because a slow sampler, you just can't do many planning steps in the background, and we want to do as many planning steps as is feasible. So these are really 4 properties I think are important. The data efficiency one is maybe one of the most important ones. And so the strategy that we pursued was memory-based. So that's what this REM model was. And let me just tell you what I mean by memory-based model. Let's say, for example, kernel density estimator is a great example of a memory-based model. And these models are promising in particular for their data efficiency. Okay, so what is the kernel density estimation? I mean, I guess probably most of the people in the audience know what that is, but here really what you're saying is I have seen T samples so far, and my density is going to be how similar I am to those samples according to some kernel K. So let's imagine, you can think of this like a mixture model, where the mixture centers just correspond to samples you see so far, and you have uniform weighting across all samples, because how the points samples are clustered is going to give you the density you need. So I kind of have this standard KD diagram at the bottom right, and then I actually have an adjusted model when you start removing centers. Okay, so a nice thing about these memory-based models is, we'd have all these nice properties of kernel density estimation, and it is data efficient, but it also allows us to do conditional distributions really easily. So we can define our kernels to be these product kernels, and then it's really easy to ask questions like, what's the distribution of our next states and rewards given a state in action, just with this very simple formula. Okay, so I know that I'm running out of time here, so I'll just hurry up a bit. And the other thing that's really great about these memory-based models is that we can ask lots of different conditional questions. So I don't just have to ask from the stored set of samples, not just probability of next state reward. I can actually ask predecessor questions very easily as well. So the issue, of course, of using this out of the box is that we can't store all the data. I mentioned that before. This is almost like an experience review strategy, but then adding sampling on top of it, but we can't store all the data. So the model that we pursued is a very simple modification where we just selected representative prototypes. And the innovation of beyond just selecting prototypes is because we know we're learning only conditional distributions, we have a nice algorithm that can incrementally compute a reweighting once we select representative prototypes. And this conditional reweighting is consistent and very efficient to compute. So we gave it a specific name, but really it's just a very simple semi-parametric model that really just needs to learn these reweightings and sub-select prototypes, and it becomes this very simple mixture model where the centers are prototypes. And because it is the same parametric model, it can learn really fast and it is data efficient. So I'll end up with the last slide that I have here about comparing to other models. Ignore the linear Dyna line, just look at the neural network line. So we compared to using a learned model that was a neural network model to this weighted experience model, which is our model. And both of them are using the exact same strategy, search control strategy, predecessors or priorities, but the neural network model is not able to do as well. And the main reason for this is simply that it learns too slowly. So if we let the neural network have more and more data, eventually it actually learns a good model. And if you had used it for planning, you would see a line that is doing as well as REM Dyna. But because it has this slow initial learning for that model, it doesn't do as well in terms of data efficiency. And it actually doesn't outperform experience replay because it just took too long to learn that model. Okay, so I'll end here with some what I think are some important open questions, like do we see these phenomena in other domains? Can we improve training of DQN by swapping out experience replay using Dyna? What other generative models can we consider? And really, we need some more theoretical understanding of Dyna, which has, as I mentioned, been somewhat underexplored, and there's a lot more to understand about it theoretically. Great. Thank you very much.
All right, thanks, Martha. And it's time for questions. So if you have any questions, I can hand you the speakerphone. Okay, so I think I have a question. So so in this Dyna framework, it seems as you are learning a dynamic model to do planning better, and so what kind of neural networks are you considering in the dynamic models?
Good question. So in the previous slide, for example, where we she was cutting up. So did you mean this previous slide where we compared a neural network model?
Yeah. So you said yeah.
Yes, good question. So here we didn't do anything fancy at all. We just learned an expectation model. It wasn't even a sampling model. It just said input, state, and action, and output next state and next reward. And it would be expected next state and expected next reward.
Okay, thanks.
Hi, Martha. Thank you for the wonderful talk. I'll make a confession. About 4 years ago, I tried doing Dyna. It was one of my favorite approaches. I was obsessed with Dyna and tried every kind of generative model we had at the time and just could not get it to work. So I'm very inspired to maybe retry it again. So I wanted to actually just ask a question about Dyna versus Dyna 2, where the tree search comes into play, and sort of maybe your thoughts around Dyna versus Dyna 2 when we put the model into play.
Yeah, it's a great question. I mean, you're right that there are others, Dyna-like paradigms that we can consider that we might have that then be improved. So here we were just considering the most basic variant of Dyna, where we weren't considering any multiple steps to the future, and we weren't considering, like you're saying, what they do in Dyna 2. I imagine that some of that criteria for some of these other Dyna-like paradigms could be a little different for the generative models. But I think that the same question, the search control question, should arise there as well. So, whether you do this one step, it matters a lot about where you're actually simulating, where you're going to spend your time simulating from, because there's no point in simulating experience from somewhere that you already have accurate action value estimates. What you really want to do is simulate experience from where you don't have as accurate of action value estimates. So for other planning strategies like Dyna 2, I think that's still going to be a critical insight.
Okay, cool. So, other questions? Okay, I think that's it. Thanks, Martha, for her talk. And yeah, so this concludes our session before the lunch, and the lunch is from now until 2, I suppose, but our session will resume at 3 o'clock in the afternoon. After that, there will be 2 other talks and the discussion panel, and I welcome you all to join. All right, thanks. And thank you, Martha. Bye.